Yeah. Okay. So let me remind you. The formula we derived last time was in path integrals, and we said if you look at path integrals and you assume that the Hamiltonian has a form that's quadratic in the time derivatives, then you can convert path integrals to some form which looks like e to the is, and the natural kinds of quantities you might want to compute in field theory are of this kind. And this measure we worked out last time carefully, although we'll see often that when we compute physical quantities, then these physical quantities you can often compute just by dividing the path integral by some factor of this kind, which is e to the is d phi. Okay? So when we derived the path integral in non-relativistic quantum mechanics last time, we were pretty careful about how this measure works, right? By discretizing things and by working out the measure there. We'll start doing some calculations today, and often in field theory, we are not very careful. At least I've very rarely seen a calculation where one actually does the whole discretization and works out the measure, because often the calculations that we have to do are pretty simple, and they reduce either to doing Feynman diagrams, as I'll show you, or doing other formal manipulations with the path integral, where the ambiguity in the measure can often be fixed by the denominator. Okay? So we proved last time that this quantity, and in fact I'll repeat the proof just to get you on board again, in field theory was in fact equal to the time ordered product of the full Heisenberg operators in the vacuum, in the true vacuum. Okay? Let me just remind you how this proof went. The way this proof goes is as follows. Assume, I'm just going to quickly repeat the proof, which we did last time for non-relativistic quantum mechanics. I'm now going to repeat the proof in the case of a field theory, and that's just to make you comfortable with the fact that the derivations in field theory go exactly the same way as the derivations in quantum mechanics. Sorry, 1 second, please. Yeah. Okay. So let's try and prove this formula, okay? And just so that we are familiar with how path integrals go and how it's the same. So we derive this formula in some detail in non-relativistic quantum mechanics. We'll derive it now. Okay. Okay. So the idea is that first, let's assume, without any loss of generality, that T1 is larger than T2. There's no loss of generality in assuming this, and the reason is it's just notation. So whatever the largest time is, I'll call that T1. Whatever the second largest is, I'll call that T2, and whatever the least largest is, I'll call that Tn. Okay. So there's no loss of generality in assuming this. Okay. Okay. Good. Now let's work out the path. Let's put some boundary conditions in the very far past. Okay. So let's put some boundary condition. Let's do this path integral with some boundary conditions, which is that phi at x at some minus t, okay, is equal to something. Let's call it psi. Okay, and phi. Let's put the boundary condition, which is phi at x at plus t is equal to psi twiddle. Okay, and then later we'll take limit as t goes to infinity. Okay, so let's look at the numerator. I have not put any boundary conditions here, and you'll see the reason I haven't put any boundary conditions here is because the boundary conditions are going to cancel between the numerator and the denominator. I could just as well have put this equal to 0. That's another boundary condition that would have been fine. But as you'll see, it will not matter, provided I use the same boundary conditions in the numerator and denominator. Okay. Okay. Okay, so this is just the numerator, and then we'll see what the denominator does. Okay, okay. So now the main point is that we can work in field theory. A basis of states by taking the field, okay, and saying say you take the field at time 0, and you say by saying that phi of x at time 0 into psi. I have to find some notation. 1 second. Let me define some notation, which is, let me call this capital psi. Okay, I'll try and call this capital psi, just to indicate this is different from this phi. And the reason it's different is because this basis is given by 3 vectors. Okay, what you have here is an operator acting at time t equal to 0, which is our, the Schrodinger picture operator, and this is equal to so this is the basis of states. These are eigenstates of the field. This is exactly like the position eigenbasis that you would have written down in non-relativistic quantum mechanics. Okay, you can, when we write down the position eigenbasis, we choose the operator, but we usually also have to choose the time at which the operator acts. Here I've chosen this operator to be at time t equal to 0. Okay, and this is the eigenvalue, but the eigenvalue here now corresponds to a function of x. Okay. If you really want to think of non-relativistic quantum mechanics, you can discretize this function. Okay. So you can think of this function as being on a lattice, and then this is really like having, if you have n points on the lattice, it's really like having n position vectors. Okay. So you can think of this as a vector, okay, of n positions where you have n points on the lattice. Okay. So this is a basis of states. Okay. So this, now you see this eigenstate, it tells you that you're evolving from the state psi, okay, to some other state in the future, which is psi tilde. Okay. So now this path integral you can break up into the following way. Okay. You can break it up as the integral from phi of x minus t is equal to psi, okay, to phi of x. This, remember, this is the smallest time is t1, is tn, and let's call this equal to phi n. Okay, this is the first part of the integral. Okay. And we have e to the is, and we have d phi. Then, remember, what is this integral doing? This integral is telling you need to integrate over all configurations in space-time. So I can break it up into integrals that integrate you from minus t to this tn. Then you have an integral, and I have to write a little bit more. Okay, so you take this integral, and then you do another integral from phi of x tn is equal to phi n x to phi of x tn minus 1 is equal to phi n minus 1x. Okay. Now I've just broken up this integral into 2 parts, but this is okay provided I also insert an integral over d phi n x here. So because when I put this integral over d phi n x, it's as if I'm doing the integral with no boundary condition here. So this is like doing the integral from minus t to tn minus 1. Okay, that's because I'm integrating over all boundary conditions here. Okay, now I also have an insertion of phi of x and tn, right? But phi of x and tn here is just this phi n of x, right? Because at tn I've said that phi of x tn is phi n of x. So I have to put here also phi n of x. Okay, and then I can keep going like this. So this is an integral over d phi n of x. This measure is slightly different from this measure. This is a measure over all fields in space-time. This is a measure over all fields only on space. Okay. In non-relativistic quantum mechanics, so this is also a functional measure, but it's a functional measure only in space. Okay, whereas this measure is in space-time. Okay, and I can keep going like this all the way till I have an integral, e to the is from phi of x t1 equal to phi 1 to phi of x capital T is equal to psi tilde. These are of course functions of x. Okay. And I have here an insertion of phi 1 of x, d phi 1 of x. And I also have here an integral d phi. Okay. So, this formula looks a little complicated, but it's not very complicated. And there are dots here. Okay. If you just think of what I'm doing in the formula, I'm saying that look, I have to integrate over all fields in space time. I can choose to integrate over all fields that take some given value at the time Tn, which is phi n, and then also integrate over d phi n. If I want, I'm just splitting up the integral into two parts, and then I do the same thing. So I cut the integral at Tn minus 1 and all the way and also at T1. Okay, that's what the dot say. Yeah. Okay. Now we can ask, so this is the answer for the numerator, right? Okay, now we can ask what is the interpretation of this, but we know what the interpretation of this is. The interpretation of this is just that you insert the field psi, you look at the state which is psi of x, the eigenstate psi of x. Okay. So you have psi of x, and then you insert e to the ih minus ih into Tn minus t. Okay, that's the evolution from, sorry, Tn plus t. That's the evolution from Tn to plus to minus t here. Okay. And then you put this field which is phi n of x. That's what this path integral is doing. Just this path integral from here to here. It's giving you this matrix element. Okay. But then I'm multiplying this with phi n of x. Okay. This is the number. This is not sitting inside the matrix element. Then I have here again this phi n of x and going up to phi n minus 1. Right? So I have phi n minus 1x, phi n of x. This time I have e to the ih minus ih Tn minus 1 minus t. Okay. And then I go to, I'm running out of space. Let me write on top. And I can keep going. Then I multiply this with the phi n minus 1 of x. This is multiplied, and I keep going. Okay. And then in the last, I have phi 1 of x. And then I have e to the minus ih capital T minus T1. Okay. And then I have this psi tilde of x. And I have this phi 1 of x sitting here. And of course, I have a phi 1 of x here and so on. Okay, I'm not writing that matrix element. And then I have an integral over all these guys. D phi 1 of x and so on up to d phi n of x. Right? Okay. Now look at this object that's sitting in the middle, which is phi n of x, phi n, phi n. Phi n of x times phi n, phi n. This is exactly like inserting the Schrodinger operator phi n of x at time 0. Right? So this you see, even though here I'm integrating over d phi n x, I can remove these integrals completely because it's like just saying that dq q is the operator q hat. This is a true statement, right? Okay. So this is like as if you inserted the operator phi n x at this point here. Remember here in the path integral, you get answers naturally in the Schrodinger picture. Okay. So this is phi n x inserted at time 0. So what we've now got is a psi of x e to the minus ih Tn minus t. Now we've got phi of x. Now we've got e to the minus ih Tn minus 1 minus Tn. Another insertion of phi of x. This is just the operator phi of x. Okay, I'm not writing a time. If you like, you can write phi of x t equal to 0. phi of x0, phi of x0. This is the operator. Because it's a Schrodinger picture, it's all at time 0, and so on. Okay. And here in the end, we have e to the IH capital T minus T1 phi of x0. And, okay. And the final state is psi tilde of x. Okay. Okay. Now these operators are all at time 0, okay, but you have all of these e to the minus IHTs. You see how these e to the minus IHTs combine. Here you have e to the minus IHTN, here you have e to the IHTN. This evolves this operator from 0 to Tn. Okay. So now in the end you get e to the IHT, which is sitting here, acting on the psi of x. Okay. Then you get phi of x Tn, which came from here. And similarly, right, all the way, phi of x T1. And on the left hand side, you have e to the IHT acting on psi tilde x. Okay, that's coming from here. Now these operators are naturally time ordered. You know, notice if I had chosen a different time ordering, if the time ordering had been the opposite, this path integral I naturally have to cut in different times in the order at which I start, okay, to be able to interpret it in this way. So you can check that, you know, if you had chosen a different ordering, of course I would have got a different ordering of operators. Okay. So the path integral naturally time orders the operators. Okay, good. Now we're almost done. You see, this doesn't quite look like what we want. However, notice, remember that this time evolution with the true Hamiltonian of any state, this time evolution, remember, we think of this as omega That's because everything else, you know, oscillates very rapidly. So of course, this is not strictly true as an equation. That's why I wrote tilde. But it's true provided I integrate with some smooth functions of, you know, that's it here. Provided I integrate with some smooth functions, it's true. Okay, so this is true as a distributional statement. Okay. Okay. So, you know, terrible. Okay. So now you see that both in the numerator and the denominator, I get from here the vacuum, I get from here the vacuum, okay, and I get in the middle, you know, these boundary conditions which are irrelevant. So the numerator is just equal to the vacuum, you know, the vacuum times this guy psi tilde, okay, times the vacuum times the time ordered product of phi xt1 to phi xtn, okay, times the vacuum, and then we get here again the vacuum times psi, okay, which is this other boundary condition. This is the numerator. Okay, the denominator is obviously the same thing but without any of the time ordered products. So it just cancels off these factors. Okay. The denominator is just equal to omega times psi twiddle times omega times psi. Okay. Therefore, if you evaluate this path integral, this ratio, you're just left with something that's meaningful, which is just this guy. Okay, so that proves this formula. This proof we already did in non-relativistic quantum mechanics last time. I just want to show you how it generalizes in exactly the same way to the case of field theory. Okay, are there any questions about this? Why are we writing what in terms of what? This one. This one comes because you see, let's say you insert a complete set of eigenstates here. Then what will happen is this will look like some integral over this. Okay, and now the thing is that all these oscillations, you know, so what you have here is e to the int integrated with some overlap of en and psi. Okay. Now, because this is very large, okay, what will happen is that you will find that these parts, unless En is 0, these parts oscillate very rapidly and they'll all decay very rapidly. But for the case where En is 0, that part will survive and that part remains here. Okay. So that's the reason why this happens. It's the same kind of argument we gave in when we did the canonical formalism. Okay, so this is an important formula which we'll continue to use. Okay, let me say one or two more things just about these correlation functions. Okay, so these path in what we did here, we were a little cavalier about the I epsilon prescription. Okay, so I want to explain that a little bit. In fact, this path integral, if you really try to do the, what was that? Okay. Okay. I don't know where it came from. Okay. So these path integrals, if you try to do them really on the real axis, okay, then they're not well defined. Okay, and in fact that formula also, we want to take a limit where you go slightly off the real axis. Okay. So these path integrals are best defined in the Euclidean theory. What does that mean? That means that you take t equal to e, you instead of rotating on that, you take t to e to the minus I theta t. So you tilt the contour slightly, okay? And then in fact you take, the best thing to do is to take theta to be pi by 2, okay? So that you've got, you've taken t to minus I t. Okay. You see, with this formula, with this insertion, what happens is that you find that e to the is, remember s itself has some integral of L with d3x dt. Okay. Okay. Now, if I instead integrate with, you have to be a little careful of, okay. If I instead integrate over the imaginary axis, okay, then this e to the is just goes to e to the minus se. Okay. Where this se is just the integral of this, but over the Euclidean time. So all these formulas you should really write as integrals. What you should really be evaluating are correlation functions of this kind. But these are Euclidean times. Let me call them tau 1. So if I evaluate these correlators, where the metric looks like 1 1 1 1 1, it looks like a Euclidean metric, and the action has an e to the minus s, so it doesn't have any oscillatory pieces, but just has e to the minus s. Then these are just some correlation functions which are well defined. Okay. Now you can ask, how do you go from these kinds of correlation functions back to the Lorentzian theory? Right? Because in the end, we are not interested physically in answers in Euclidean time. Right? We are interested in answers in Lorentzian time. Okay. So for this, it's important to understand something about the analyticity of ordinary correlation functions like the kinds we are computing there. Okay. So I want to tell you a little bit about the analyticity of those kinds of correlation functions. Okay. First, let me just look at this is not the same as that. Okay. You see why it's not the same as that? Because there's no time order. Okay. So I just want to look at this correlation function. Okay. I want to ask what are its analytic properties. I don't remember if we discussed this earlier in class. Maybe we did, but if we did, it's good to see this again. Okay. So the way to see its analytic properties is to insert a complete set of energy eigenstates here. I should have put E0 here. Okay. And then I sum over all the EIs. I haven't done anything. I just inserted a complete set of energy eigenstates here. Okay. In fact, maybe sorry, I don't need this guy. And I think I don't need this guy also. It's useless. Sorry. Sorry, I think yeah, we don't need these guys. Last two guys we don't need. Okay. 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 Now look at how this evolves as a function of Tn. Sorry, I didn't need the guys on the edges. It's the same formula as previously, but the guys on the edges. Okay. This looks like right. This came from here. This came from here, but it's the same E1. You see this? And in the last part, you will get e to the I En minus 1 into Tn minus Tn minus 1. What I want to focus on are these factors. You will get these phi x's. Okay? You will get this between E1 to E2. You'll get these similar factors, but look at these phase factors. They all look like e to the I E1 into T2 minus T1. Okay? What is the property of these EIs? The property of these EIs is they're all positive. So energy is positive. Right? Okay. Therefore, this correlation function is analytic when T2 minus T1 is extended in the upper half plane. Okay. Why is it analytic? Because see, where can the divergence in this, where can the singularities in this correlator come from? They can only come from the large E limit, right? That's where the infinities are, from what happens at large E. Now, say this correlator is well defined for some value of t, then you see that if I take when tj minus tj minus 1, when the imaginary part. Now say I make an extension of this correlation function so that T2 minus T1, I give it a positive imaginary part. If I do that, then you see that whatever the earlier correlation, whatever the earlier convergence was, the convergence over E is now improved because I now get an e to the minus E1 times in imaginary part of T2 minus T1 and so on. Okay. Therefore, this correlation function is analytic when Tj minus Tj, when all of these variables are extended in the upper half plane. I don't have to, but if I extend them in the upper half plane, I will not get a singularity. So the singularity structure of these kinds of functions is rigid in that you can't get singularities when you have this condition being met. Okay. These kinds of correlators are called Weitmann functions. They are not quite time ordered functions. Okay. Okay. Is this clear what I just said right now? Okay, good. So now, Okay, now if T1 is greater than T2, then the imaginary part of T2 minus T1 into e to the minus I theta is greater than 0, provided theta is between 0 and pi by 2. Okay. This is just some elementary identity. That's because if T2 is greater than T1, then T2 minus T1 is something which is negative. This has some negative imaginary part, therefore I get something which is positive. Okay. Therefore, if you start with these times all in the Euclidean axis, if we start with Euclidean correlators, and rotate all times simultaneously back to theta equal to 0. Okay. So remember, I was earlier given the correlation functions for Euclidean time, tau, which was minus it. Okay. Now I start analytically continuing those correlators. Okay. So that I write the Euclidean time is e to the minus I theta tau, okay, according to that correlation function. The correlators were best defined when theta was equal to pi by 2. That's when I had this formula. Okay. Now I start looking at those correlators as a function of theta, and I take theta to be close to 0, okay, but not quite 0. I give it a small imaginary part. Okay. Then you see that that is like looking at that correlation function, okay, and extending it slightly in the upper half plane, okay, slightly in the imaginary axis. But the extension is automatically. Let me say it in a clear. 1 second. 1 second, please. So what I want to say is, then we automatically get time ordered correlators. Okay. Okay, why is that? Think of that correlation function, okay, and say T1 is larger than T2 and so on is larger than Tn, which is the same convention that we had previously. Then that correlation function is a time ordered correlation function by hand, right, because of the way I chose it. Now you see that correlation function is analytic when I extend T2 minus T1 to e to the minus I theta. Okay. So if I extend both T's with e to the minus I theta, but keep the same value of theta, you see I won't reach any singularity. Okay. So if we extend each T this is the same theta, okay, does not depend on I. Then we won't encounter any singularities. Right? With this condition. Do you see this? Okay. Conversely, if I give you this answer when t is gone to minus it completely, then I can rotate it back without encountering any singularities. I can't rotate it quite all the way back, because sometimes it might be that when I rotate it all the way back, I get some singularities. Okay. But I can rotate it almost all the way back. And if I do that, you see I get automatically time ordered correlators. Okay. Okay, do you see that? Well, if you rotate things, so generally when we think of correlation functions in quantum field theory, the I epsilon has been important for us, right? These correlation functions are generally defined with an I epsilon prescription. That's what this I epsilon is doing. This e to the minus I theta, if you rotate it all the way back, then you often get singularities and branch cuts, as you've already seen in various correlation functions that we have computed. Okay. So if you keep a slight imaginary path, then you find you don't have singularities. But and this I theta is exactly the I epsilon. Okay. Okay. You know. Well, the I epsilon prescription is contained in that you have to define. You start with the Euclidean path integral. Well, the path integral will not converge. So you start with the Euclidean path integral, which is best defined, and then you take all the times. You write the times as t e to the minus I theta, and imagine that you have theta equal to I pi, and then rotate all the answers back. Rotate them almost to the real axis, and then you'll get the correct answers. Those are Lorentzian answers. Alternately, you can start doing the path integral, but then remember you have to work on this contour, which is e to you have to take all the times to t to the e to the minus I theta t and keep a small value of theta. Otherwise, the path integral won't converge. Okay. Okay. So do you see why you get time-ordered correlators? If you do this kind of extension where you take t e to the minus I theta ti, the only correlator which is analytic is the one where you have arranged the times in this order. Okay. If it so happened that t2 was larger than t1, then the correlator that would have been analytic is the correlator which would have had t2 to the left of t1. You see that? Okay. So when you start with the path integral, where you start with something that doesn't have any singularities, it's a manifestly convergent thing in the Euclidean plane, you rotate things back, you still don't encounter any singularities, but you end up on the correlator which is time ordered. Okay. Okay. Let's say I started with the Euclidean correlation function, and it happened that t2 was larger than t1. Say it happened, but I still wanted to get the answer with t1 to the left of t2. Can you say how I would get that? What would I need to do? Say we were given. Let me call it tau 1. This is the Euclidean time. Okay, not this is the Euclidean time, which is you can think of as imaginary times the Lorentzian time. But I'm giving it to you as a function of tau. So if you like, you can take tau equal to minus it, and you can start trying to rotate. By this I mean I've done the path integral in Euclidean time, but I can do it for different times. I have this analytic function, and I want to get. We want to get. Let's do it for a 2-point function, okay? Okay, and we want to get but t1 is larger than t2. So if I give you this answer as a function of tau 1 and tau 2, and I want to get this anti-time ordered correlator, what should I do? Rotate the other way. Well, okay. Generally you can't rotate the other way, but let me add a few more points so you can't just rotate the other way. Okay, t1 is larger than t2, but t1 is larger than t0. Okay, so these 2 points are time ordered. This point is out of time order. Okay. Let me call this x0 tau 0. By the way, these Euclidean correlators, they never depend on ordering. Euclidean correlators, there's no notion of ordering because their things just commute. Okay. Okay. So let's say I give you this answer. I mean, whatever, I compute the path integral with this answer, with this product of things. And now I ask you to get this answer in Lorentzian space. This is a well-defined quantity, right? Nobody said you can only consider time-ordered products. This is just a product of operators. How will I get this answer? Any ideas? Okay, good. So what should I do to get this ordering? Okay, good. So how should I order the thetas? Okay, good. You guys have got the idea. So basically the point is the following, right? You think of this function, which is e to the I theta I, okay? And you make sure that e to the minus I theta I, right? You just make sure that imaginary part of, so let's call this ti of theta. Okay? As you rotate this, as you rotate, so you want to evaluate it as, you want to take the limit where all the thetas go to 0. But take the limit by ensuring that the imaginary part of t3 theta 3 minus t2 theta 2, okay, is larger than 0. Sorry, not t3. What did I want on the right hand side? t0. t0 theta 0 minus t1 theta 1 is larger than 0. And the imaginary part of t1 theta 1 minus t2 theta 2 is larger than 0. Okay. So I can rotate them, but I can, instead of rotate, you see, if I kept all the thetas the same, then the imaginary part of t1 minus t2 would not have been larger than 0 because t2 happens to be smaller than t1. Right? So the imaginary part would not have worked out correctly if I was keeping all the thetas correct. But there's no rule that says I have to rotate all the thetas to 0 at the same time. I can rotate the thetas to 0 in different orders. If I rotate in different orders, provided I maintain this condition as I take the thetas to 0, I'll get the correct ordering. Okay? So you can always take the thetas to 0 in different orders, and when you do that, you'll get, whatever ordering you want. So if you're given the full Euclidean answer, you can always use that to get, answers in Lorentzian space by doing the right kinds of analytic continuations. Yeah. Okay, good. Okay, good. Let's now. Okay, so this was just meant to say how you get path integrals in Lorentzian space, starting with, where did the I epsilon go in path integrals? This is where the I epsilon goes. Okay, it sits here, and you can also have more general I epsilon prescriptions. So the usual I epsilon prescription is just to do this, just rotate all the TIs together, and as we'll see, that will give us the usual I epsilon prescription. Because what you have done here is you've just rotated the time contour of the entire path integral. All times you have rotated and you're making them run as e to the minus I theta t. Okay, so that's fine. And that's a simple way to do the path integral, where you just make every time in the path integral go on a slightly tilted axis. Okay, actually that's, yeah, like this. I always get confused. E to the minus I theta, yeah, like this, right? We'll work it out in a second, huh? Yeah, theta was pi by 2, but now I want to take theta to go very close to 0. So I want to be, yeah, okay. We'll work out the sign in a minute. By the way, I should say I try to get the signs correct, but when you derive this yourself, just be a little careful about the minus I thetas and so on. Okay, there's some possibility I've made a mistake of sign. Okay, but okay, good. So let's we'll derive it in a minute.
Can you derive this like the time order correlation? On one side you have the correlator, which is on the other side you have a path integral. You have not put the
No. We had the epsilon prescription. Where did I say we didn't have the epsilon prescription? In the first formula we wrote. No, that formula, when you define the path integral, you should define it with an epsilon prescription.
In the derivation, where does
it goes into the fact that it went into the saying that the path integral looked like e to the minus IHT. of something. It also went into this part where we had, where we said that we are landing up on the vacuum. Landing up on the vacuum requires that. But even making the path integral well defined to get the e to the minus iht requires you to have some slight imaginary part, because even correlation functions, matrix elements, are well defined only after you give a proper I epsilon prescription. So in field theory, these I epsilon prescriptions are always important. So, the path integral looks like some badly divergent quantity in general, because it looks like you're summing over lots of imaginary phases. So to make your integrals convergent, it's important. It's important in many places, not just in the vacuum. For instance, when we derived the e to the is form, we actually started with the path integral that was written as an integral over phase space. Then we did the quadratic part of the integral to go from what looked like pq dot minus h to e to the is. To do that, there was a Gaussian integral in P, which was in fact a divergent integral, but we regulated it. And so all this is implicit everywhere, that we have an I epsilon in doing the path integral. We had e to the I p squared, which we did integral with, and that only works if you have the right I epsilon. Okay, good. So let me say something about Gaussian integrals in many dimensions. All of basically in path integrals you only do Gaussian integrals. You never do anything else, because that's all we know how to do. Okay. Just like in field theory, we only do free fields and perturbations about free fields. Sometimes you can do more sophisticated things, but most of the time you're just doing Gaussian integrals. Okay. So say we have okay. So say we want to do e to the minus x dot a dot x. Okay. This is a matrix. Okay, so we have xi, aij, xj, and we are summing over all the i's and the j's. Okay, and we have plus bi xi. So this is just an integral. All the xi's are integrated from minus infinity to infinity, and we have some matrix of this kind. Okay, and there's a standard formula for this, which is just that this is equal to e to the minus b transpose a inverse b by 4 into square root of 1 second 1 by det of e by pi. Okay. Okay. This is a simple formula. It just arises by doing a change of basis here. Okay, and that's because when you look at this formula, you see it doesn't depend on what basis you're doing this in, right? You can make a change in the integration variables, so you can always make an orthogonal transformation. So as if these are complex variables, you can make some unitary transformation so as to diagonalize these guys. Okay, and when you do that, you find that make a change of basis. Some xi tilde, and then this just looks like xi tilde times ai xi. Okay, so that this matrix just gets diagonalized, and these are the eigenvalues, and this still looks like bi times xi tilde, where these are the elements of this b in this different basis, right? Okay, but now this integral we know how to do, because you just get square root of pi by right. Okay, and you have to complete the square, so you get e to the minus b twiddle I times squared by aii, and there's probably a factor of 4. So this answer we have, right? But this answer is on a particular basis. Of course, I can go back, and if you go back to the original basis, this is just a product of aii by pi, which is just the eigenvalues of the matrix A by pi. And then you have here, this is just b times A inverse times b by 4. So this is the key formula that you need to remember when you do path integrals. Okay? Okay, good. Are there any questions about this? Okay, one more formula you should remember, or maybe which is, basically just follows from this, but let me just write it down once more, which is this, that remember this, which is e to the minus ax squared into x squared dx. Where did this come from? This just comes from differentiating this formula with respect to A. Okay, you just differentiate it once with respect to A, you'll get this answer. Okay, good. What's the vector generalization of this is that if you look at dxi, and you insert xm, xn, e to the minus you can also get this formula by just functionally differentiating with respect to b. Okay. Okay. Okay, so this formula is a derivative of this, but this is the other formula that you need to keep track of. Yeah. Okay, good. So let's apply this to quantum field theory now. Okay. Let's look at a free scalar field and see what we start getting with this. Okay, let's say we start with the free scalar field and we have integral d phi e to the minus so often what we usually have is that s is equal to integral half times d mu phi squared, okay, minus m squared phi squared, right? Okay. However, this answer, this integral can often be integrated by parts if we just want the action, and you can write this as half of integral phi times, okay, minus of box minus m squared times phi. Okay, so you can take this derivative and you can move it to the other side and you'll get something like this. Okay, okay, good. So let's say, by the way, we are doing this in Euclidean space. Then we would get 1 second, phi squared. Yeah. So if you're doing this in Euclidean space, then we would find. So let's say we wanted to do this. So the Euclidean action here looks like half of integral phi, okay, times minus box Euclidean, but with a plus m squared times phi. Okay. This has to do with the way we've, with the way our sign conventions work. Okay. But one simple way to remember that this is the way remember our sign conventions have been slightly funny, where we have taken, the mostly negative metric. Okay. So this guy has, plus components for the spatial directions and a negative component for the time direction. Okay. When you take the Euclidean thing, you just get minus of this whole box, because the time direction also gets a minus component. The spatial directions already had a minus component. One way to remember this is to just realize that if you take phi to the e to the I kx, okay, in Euclidean space, then minus of box c, box gives you something which looks positive, because when you act with box, you get ik times ik, so you get minus k squared, and minus of that gives you something that's positive. So this whole thing always is positive, has positive eigenvalues, okay, which is what you want the Euclidean action to be. Yeah. Okay. So say we now want to compute minus half times phi of minus box e plus m squared phi. Okay. So what would this be? Okay. Using the formula that we have, we would just write this as 1 by square root of det of minus box c plus m squared by pi. Okay. Okay. In momentum space, this would just look like the product over all k into 1 by square root of ke squared plus m squared by pi. Where this is now a product over all Euclidean momenta. Okay. In this lecture, I don't want to get into the details of how you could regulate this guy, okay, because for everything we are going to do, this determinant is going to cancel. Remember, in all the formulas that we always had e to the minus s, and we had a division by e to the minus s. Okay. So I'm not, you could say, well, this quantity looks like it's some infinite quantity, and it does look like it's an infinite quantity, and you can ask, well, is it infinite or is it zero? Because you have a product over all these momenta, right? And this product is a continuous product, and so you could say, this doesn't make any sense, but you'll see whenever we compute something, whenever we compute a 2-point correlation function or a higher point correlation function, this product, this infinite functional determinant, will always cancel between the numerator and the denominator. Okay. So for the purposes of what we are doing right now, we don't have to be careful about how to regulate it. Sometimes you do have to be careful about how to regulate this determinant, okay, in some cases, but those discussions are beyond the scope of what we are talking about. Okay, good. So let's now use the second formula that we wrote, okay, and let's compute the time ordered product. Right? So let's ask, what happens if you try to compute d phi of x1, phi of x2, e to the minus half, e to the minus se, okay, e to the minus s, and we divide by integral d phi e to the minus s. Okay. This is the kind of answer that we wanted to compute. This is now going to give us a Euclidean correlator, but this is the answer that we wanted to compute. Okay, good. So you see, it's basically a question of dividing that formula with this formula. Okay. And you see here b is set to 0, and in that the functional determinant is going to cancel. And all you're left with is just the inverse of this guy. Right? So what will you get? Here m and n are these points x1 and x2. Right? So this is equal to g of x1, x2, where what equation does g of x1, x2 satisfy? G of x1, x2 is that quantity which, when multiplied with the matrix A, right, gives you the identity. Right? So it is something which satisfies minus box plus m squared on g of x1 x2 is equal to delta 4 of x1 x2. Okay. Okay. So this so far is all in Euclidean space. Okay. So we can write down what the 2-point function is in Euclidean space, and the 2-point function Euclidean space is just okay. Okay, now let's see if we can try and get our epsilon prescription correctly. Okay. So remember that I want to take TE, the Euclidean time that enters here, to be minus IT, because I was in Euclidean space and that was by prescription minus IT. Okay. And KE0 to be minus IK0. Then what happens is that TE times KE becomes minus K0 times T. Okay. Okay, good. So then this Green's function I can think of as giving you 1 second please. So this g of x1 x2, this was so far in a Euclidean answer. Okay. But now I can say, well, let me think of these points as being in Lorentzian space. So let me think of this T Euclidean as being minus IT and this KE being minus IK0. Okay. So now instead of doing an integral over dke, I'll think of this as doing an integral over dk0. Okay. And what I'll get will be minus I integral d4k e to the minus I k dot x, where this is now the Lorentzian k. Okay. And then I'll get here minus k squared plus m squared. Okay. Why did I get a minus k squared? Because the way our sign convention went, ke squared of course has the k spatial square positive and the k0 square also positive. Okay. For us, we want, when you write ke as I k0, you'll get the time square negative and the spatial square positive. In the conventions we've been using in all of our course so far, we want the opposite convention. So that's what we write as minus k squared. Right? Okay. And now I want to do the integral of d4k. So k is equal to, let's see if I got this sign right. What happened to this sign? K was k0 was equal to IKE. 1 second, guys. Sorry. I have d4ke and ke is equal to minus ik0. That's why I also have minus I here. Yeah. And this just looks like I times an integral of d4k times an I with a plus I now with a k squared minus m squared. Okay. With an e to the minus I k dot x. Okay. Now you might say, what happened to the I epsilon? Well, remember the k integral is still running over where the ke integral was running from. So the k integral is still running along the ke contour. Just by making a change of variables, I haven't changed the contour of integration. So k0 is equal to I times ke, right? And it runs from minus infinity, ke runs from minus infinity to plus infinity. Right? So in this formula, as I've written it, the integral over d4k actually runs from minus infinity to plus infinity. Okay. So the K0 integral runs this way, is running this way. Okay. Then I can rotate it back to the real axis. And when you rotate it back to the real axis, then you'll find that the integral runs this way. Okay. Is this the right way we want it to run? I think this is the right way we want it to run, right? Because the pole, the P0 squared minus P squared second, let's see if we got this right, minus P squared. So in this, what happens is P0 develops a small negative imaginary part, which is correct, right? So the pole lies below the right one. So I think this is correct, yeah? Okay, so when we rotate back to the real axis, we get this contour of integration, okay, which is the same as the I epsilon prescription. Okay. So you see, if you start with a Euclidean answer, and then you rotate the Euclidean answer back to the real axis, so this Euclidean answer you now have, it's a function of all times. And now you can try and rotate this Euclidean answer back to the real axis. When you do that, you see you will get the I epsilon prescription. Okay. But the correct way of getting the I epsilon prescription, the path integral, is to start with the Euclidean answer and rotate it back to the real axis. Okay. So what you really get in the path integral is that the time contour is shifted this way, but that's equivalent to this. Is that okay? Okay, very good. Let me say something about higher point correlators. We have only one lecture more. So by the way, just organizationally, we agreed to have the exam on 1st May, right? Can we do half a lecture on Monday, or that's you have other exams? 29th. You have an exam. What about Friday? Okay, I'll try to finish next time, but I have a little more material. Let's see what we can do. Let's see. Okay, maybe we can finish next time. I'll try and shorten the discussion. Okay, we can try and do that. We'll see what we can do. Okay, I kind of want to do at least one lecture on scalar QED. That would be a reasonable stopping point. It would have been good to do two, but let's at least do one, and maybe we'll stop next time. Yeah. Okay, good. So let's consider higher point correlators, and then we'll be done with field theory. And I want to show you how you get back Wick's theorem from path integrals. Okay, one thing that's very often used in path integrals is the generating function. What is the generating function? The generating function just says, let's say I had a path integral S. Okay. This is the original action. I've just defined the path integral with this additional term added, where this was the original action. Right? Okay. Now let me ask, what happens if you look at del n of z of j by del j of x1, del j of xn, 1 by z of 0, and then you set j equal to 0. So you differentiate this functionally n times, and then you set z equal to 0. Well, that's very simple. That is, it's just that, you differentiate this n times. So this is just manifestly equal to e to the is times phi of x1 times phi of xn. Maybe I should put factors of minus I to the n here. If I put an I here, then I should put factors of minus I to the n here, so that I get a 1, and then d phi okay, and that's because this is z of 0. Okay. This is, so this, it's of, if you know this generating function as a function of j, then you can get all these correlation functions. Okay, so for instance, that formula we just derived, you could also derive it by computing the generating function and differentiating it functionally. The same thing. Okay, good. This is just something you should know because it's used a lot. In practice, you often end up using that formula that we wrote there, which is that integral of x squared is a inverse is basically the same as what you get when you do the generating function. Okay, but you should be familiar with this. Okay, now I want to say, consider the interacting theory. Okay, so I want to give you an example. Since we've been discussing the scalar theory, okay, let's add. So let's consider S is, this is still the Lorentzian S, of course. So now, by the way, I'll just do things directly in the Lorentzian space with this e to the is. Okay, as I said, to really define things correctly, you should go to Euclidean space and rotate back. But the net effect of that, for our purposes in perturbation theory, is just to insert an I epsilon. Okay? So we can work with the I. Now we've understood how the I epsilon prescription comes out in great detail. So now we can just work with the Lorentzian theory and just make sure we use the right I epsilon prescription for the propagator, and as you will see, for the higher order perturbation theory as well. Okay. What I now want to show you is how, when we consider an interacting theory, you will automatically get back Wick's theorem and the expansion that we had when we did this canonical quantization. Okay. Okay. So okay. Okay, good. Now, let's say I had this. Then, I want to evaluate now e to the is of, say, some correlation function. Okay, maybe of a 2-point correlation function. Okay. Well, maybe I should say one thing before I say something about the interacting theory. Sorry, guys. Sorry, we'll come back to the interacting theory. Let me say something about higher point correlators first using the free theory. Okay. Sorry, I'm going to go back to that, but I forgot I wanted to say one more thing about higher point correlators in the free theory. Okay. Say we want to get higher point correlators in the free theory. By the way, we know how we get them in using Wick's theorem, right? In Wick's theorem, all we get is the sum of all possible contractions when we are computing the vacuum expectation value of higher point correlators. We want to see that we get the same answer here. So say, for instance, we are computing, well, let's compute first for this action, let's compute what this generating function is. Okay. So let's ask, with S is equal to half d mu phi squared minus m squared phi squared. What that generating function is where I have an e to the I. So let's evaluate what z of j is. Okay. Well, what z of j is just comes by using the formula that we had previously. Let me see if I can get my signs right. Which is just that when we are trying to ask for e to the is plus ij times I j of x phi of x with the d phi. Okay. This is a Gaussian integral. Okay. So we just do the Gaussian integral as a function of j. We'll be a little cavalier when we do this Gaussian integral. As I said, we should rotate this to Euclidean space and make it e to the minus is and so on. Let's just do it right now by being a little careless. And remember the formula we had, which we erased, was that e to the minus ax squared plus bx was dx was e to the minus b transpose a inverse b by 4 square root pi by det a. So, here our a is just this. This just looks like phi half phi into minus box minus m squared times phi. Okay, d4x. So this is the action, and let's just take a to be I times this quantity. Okay. Did we need a half here? Or maybe when I wrote the formula, I think we needed a half here. Okay. Sorry, when I wrote this formula, none of you noticed, but I think I needed half ax squared here. Okay, we'll get the correct normalization if there's a factor of half here. I think that is correct, right? Or not? Okay, normalization is going to be completely unimportant because it will cancel. Okay, where we can derive it, but oh, sorry. I don't need the half. Okay, maybe I don't need the half. Let's derive it. E to the minus ax squared. Let's square this integral. So you get e to the minus ay squared dx dy. Then it looks like e to the minus ar squared. So I've just squared the integral I squared. So it looks like a to the minus ar squared into r dr d theta. So this looks like 2 pi times e to the minus ar squared r dr, which looks like pi times e to the minus ar squared a into z into dz. And indeed, I don't need it. So this just gives you pi by. Okay, sorry, you're right. I don't need it. What I was writing was correct. Yeah, sorry. Sorry, I just want to. I'm going to take 5 minutes extra so I can finish at least this discussion of path integrals here. Okay. So we just apply this formula here, and the important thing is that what you get. Let's see if I can get my signs correct. B is equal to ij, so I want a minus times ij times a 1 over minus box minus m squared. And then I want a j. This is a ij ij, b is minus, so I get a minus b minus into ij times ij times 1 by box minus m squared and going to minus I minus I. Getting on to minus I here. Okay. I'm a little confused about whether I got all the signs correct, but I think this should be e to the minus j of x1 times g of x1 x2 times j of x2 by 4 and with some factor here of an overall factor of I, okay, or minus I, which I'm a little confused about right now. Let's see. When you differentiate this with respect to ij of x1, sorry, there should be a plus sign. There's an A inverse. There's a minus A in the formula. Okay, let's try. So this should be a yeah. So I should have written this as minus of. So this minus is yeah. Okay, sorry guys, there are many signs here, and unfortunately I'm running out of time, so I'm not going to try to fix the sign. The many signs have to do with whether we define G, is the inverse of box plus m squared. Okay, so there's a minus sign here as well. And there's also minus sign. I'll tell you what the sign is next time. Okay, but let's just work with a plus or minus here because it's not going to be important. Okay. Okay. So the main point is when you differentiate this twice with respect to j, okay, then you find that one second, guys. This is ij and is. Okay. You see, I'm sorry about this sign. I'll try and figure it out next time. It's not. It's unimportant. The main point is that we already know that delta 2j by del j of x1 delta j of x2. This is equal to g of x1 x2. Okay. Okay. Now let's say I try to differentiate this guy. Okay. But I try to differentiate it 4 times so as to get a 4-point correlation function. Okay. So let's say I try to compute delta 4 of z of j by delta j of x1, delta j of x2, delta j of x3, and delta j of x4. Okay. And there are various i's and so on, but those will not be important. What I want to show you is how the combinatorics works out. Okay. So what happens is, you have here an integral, okay, but these are all just some dummy variables. Okay. So what happens is you will get here, g of x1 x2 times g of x3 x4. That's one possibility. But these derivatives could also give you other possibilities. So you'll also get other possibilities. So you'll also get plus g of x1 x3, g of x2 x4. Okay. And you'll get one more term which will be g of x1 x4 times g of x2 x3. Okay. So what I want to tell you is that by looking at this derivation up to the i's that I'm sorry we have not been careful of, you will get exactly Wick's theorem because this g is just the contraction, right? So what you get here is when you compute the 4-point function, you get the sum over all possible contractions, which is 1 with 2, 3 with 4, 1 with 3, 2 with 4, or 1 with 4, 2 with 3. Okay. And similarly, if you just look at higher point functions, then Wick's theorem, which just tells you will get products of contractions, will just emerge here for the free theory. And the reason it will emerge is that in the free theory, the generating function is Gaussian in J. Okay. So you can only get products of J when you set J equal to 0. Remember, in the end, I'm going to set j equal to 0. So this is at j equal to 0. Okay. Gives you this. And of course, I have to divide by 1 by z of 0. Okay. So when I do 1 by z of 0, all this functional determinant cancels away, and I get this. I'm sorry for being a little rushed, but I hope you get the main point of how you get Wick's theorem. Should I explain this point, or is this roughly clear? Okay, good. Let me go back to the interacting theory and then I'll stop. So what we learned here in this slightly rushed thing is that higher point correlators in the free theory give you Wick's theorem, okay, just like you get in the free theory by doing contractions. You don't have to prove Wick's theorem. This is a way of deriving it from the path integral, if you like. Okay. Wick's theorem is a slightly stronger result because it holds at an operator level. This is telling you what vacuum expectation values are, how you get the sums of all contractions. Okay. If you now ask for some correlation function here, well, what does this correlation function look like? This correlation function looks like the correlator of e to the I s naught times e to the minus I lambda phi to the 4 by 4 factorial times phi of x1 to phi of xn d phi, right? But this is as if I was computing the correlator of this object in perturbation theory using only the free theory. Right? So this is what in the canonical formalism I would have called, the vacuum expectation value, okay, of the time ordered product of e to the minus I h I, which is this object. Okay, so this is integrated here, sorry, because this is the integral of hi of t, okay, and with phi of x1 t1 phi of xn, okay, this is the thank you. So you're right. When I divide this with e to the is d phi, this is not the free vacuum. This, you see, this always gives you correlators in this vacuum. Okay, sorry, you're right. This gives you some correlators in the free vacuum. When I divide this with e to the I if you look at what the denominator looks like, I'm sorry for rushing this. What you get is e to the I s naught, and you get this term, and that term is you should interpret as in the free vacuum time ordered product of e to the I hi dt. And indeed, the formula that we derived in the canonical formalism was that the vacuum correlation function of phi x1 to phi xn in perturbation theory looks like you evaluate in the perturbative vacuum the time ordered product of this object in the numerator and divide by this. And you see that's exactly what we're getting here. So the path integral is giving us a quick way to derive this formula that we spent some time deriving in the canonical formalism. Okay, do you see why it works out? How you get back, perturbation theory in Wick's. So in the end, the upshot is that the path integral leads to exactly the same perturbative expansion that we had previously. Why? Because the path integral tells you how should you evaluate all these correlation functions. Well, you should evaluate them using this kind of a formula, right? And that's just summing over all possible contractions. And you see you get exactly the same perturbative expansion, and you also get this cancellation by vacuum bubbles, which we had in the canonical formalism, which came from the e to the is. Okay, I'm sorry for rushing, but the upshot is there's no new result we are deriving. I just want to show you how from the path integral you get back the Feynman diagram expansion that we got in the canonical formalism. In fact, it's a little simpler because you automatically get this division by vacuum bubbles and so on without having to argue for it in some more complicated way. Okay, let me stop here since I'm already 10 minutes over time. And next time, we'll have some discussion of how to apply path integrals to understand scalar QED. Are there any questions about this, sir? I'm sorry, this was a little rushed, but I hope this is somewhat clear. If it's not clear, you can ask me next time. Yeah. One place to read about this, this is discussed in Peskin and Schroeder, but not that well, is a book by Matt Schwartz on quantum field theory, where there's a reasonably clear discussion of this. Okay. Okay, good. Let's stop here. And next time we'll do some discussion of gauge fields.